Okay, we were at a point where we had shown that alkynes perform back-to-back electrophilic additions. So we should be expecting this asymmetric alkyne to make this molecule followed by this, and we should be expecting to see the geminal diol. Electrophilic addition across this pi bond right here. This is the most substituted carbon. That's the most saturated carbon. The electrophile, H+, goes to the saturated carbon. The nucleophile, OH-, goes to the substituted carbon. Repeats. That's what we're expecting. And this doesn't happen. Something completely different happens. Completely different. Draw that bond in. What we get instead is the product of this reaction is this. That's completely not what we were expecting. But because this is a completely different family of molecule than that, we're just going to have to accept this and use it to our advantage. This is an alkyne. We were expecting a diol, but instead we got a ketone. Ketone is a carbonyl, a carbon to oxygen double bond with carbons on both sides. So this is an sp2 carbon. I've written it out on a straight line, but really, it would help if you wrote that as a trigonal planar. Okay. All right, so how do we get from here to there? Well, it's kind of complicated. It's kind of complicated. But it all has to do with the electrons that are not holding the framework together. Okay. So this methyl, that's still there. The bond between the carbon and this carbon is still there. I get a new bond to oxygen. I have to describe a new bond. And I've lost a bond between these two carbons, so I'm going to have to describe that. But then the alarm bell goes off in that did that hydrogen come from? Because this carbon has 2 hydrogens. By the time we're finished, it has 3. That hydrogen that is on the alcohol is going to migrate. The pi bond is going to reach out and grab hold of it. Now, because you're breaking that carbon-carbon bond, the question becomes, well, which one of these 2 carbons gets to have the hydrogen? But we're going to force that question never to be asked, because the lone pair of electrons on this oxygen is the thing that's going to make this pi bond have to break. You know what? Let me do that differently. Because doing that description actually requires another arrow. I can do it simpler than that. Here's an oxygen. It has a double bond to a carbon. That carbon has a single bond to this carbon. This carbon has picked up a new bond. All I really have to do is explain where the new bond came from, yes, where the old bond went. I've got to break that bond right here between this oxygen and that hydrogen because it's not there anymore. But we do know that oxygens with 2 bonds also have 2 lone pairs of electrons. So there's a couple of ways we can do that. I can move the lone pair of electrons, force of habit, because that's what we're going to do in the future. Or I can just cheat and say those 2 electrons, that oxygen's a hydrogen bond. Go ahead and make a new pi bond. So you can describe this with 2 bonds, with 2 arrows, or you can describe it with 3. You describe it with 2, pi bond grabs the hydrogen. The hydrogen lets go of its electrons and they become the pi bond. Alternately, you can have the pi bond reach out to the hydrogen. These 2 go to the oxygen, and then a lone pair from the oxygen goes into the pi bond. New pi bond that's being made. And we find that this is something that happens in nature a little bit, but is very, very heavily influenced towards the ketone and away from this form. We're going to put a name to this. This is an alcohol that contains an alkene. And the alcohol and the alkene are attached. They're both on the same carbon. So this is part alkene and part alcohol. This is an enol. And enols rearrange to make ketones. Almost universally, I can think of 1 or 2 exceptions where the enol is stable. Most of these are not really wickedly unstable, like reactive unstable, but they rearrange. And because this rearrangement doesn't just reshuffle the electrons, like resonance is going to do when we pause for a second and pay attention to resonance. Resonance is just the electrons that are not holding the sigma bonds together moving. I've got a bond breaking here. So this process is called keto-enol tautomerism. And these two are isomers of one another, but we call them tautomers. And ketoenol tautomers favor the ketone form. And so, there will be times, a couple of times in the textbook, that we'll be just trucking along, doing something, and then all of a sudden the reaction goes wrong. At that point, you should ask, wait, was there an enol in here somewhere? Because every time there's an enol, it ends up doing what it wants to do and not what you wanted it to do. And this versus that makes complete sense. Why would this be better than that? People at home, join in. Why is the keto better than the enol form? The answer is on the periodic table. People at home, why is the ketone more stable than the enol? Nobody? Oh, I haven't got my projector on. Just a no. No, not really. Well, the answer is yes, but that's not the reason. Question back was, single bonds to carbon more stable than double bonds to carbon? By framing your answer in terms of carbon, missing the point. Oxygen is electronegative. Oxygen is electronegative. That means it is capable of pulling electrons towards itself in a covalent bond. So, look at this carbon. Why is this carbon giving its electrons to another carbon when it could be giving them to the oxygen? Oxygen sees the pi density of its neighbor and just says, I'll have that. I don't need this hydrogen. You can take the hydrogen. I'll take the electrons. Having a pi bond to an oxygen is a better bet than having a pi bond to a carbon, because oxygen's electronegative. It's supposed to have the electrons. It's supposed to have them. Okay. There is something in here that is hiding. that if I take an alkyne, an asymmetric one, and I put it in dilute acid, like dilute sulfuric acid, then I make this ketone. And that ketone arrived through an enol. What other reaction, and you can either know this by its components, its reagents, or by name, I'll take it by name. What other reaction did we use that converted an alkene into an alcohol? Because this turned an alkene into an alcohol. What named reaction turned alkenes into alcohols? Wasn't it on your homework sheets? When was that due? When's your homework? Is it done already? Did I miss it, or is it due on Sunday? It was due on Sunday, or it is due on Sunday?
Was.
Okay, so you've all done it and you've all turned it in. Okay, I haven't graded it. I'm kind of busy. Been unexpectedly busy this week. I thought it was going to be regular, but it's not. It's been kind of sort of busy. So, on that sheet that everybody turned in, there were at least 2 named reactions. How do you turn an alkene into an alcohol? Without a Markovnikov, they make the Markovnikov product without the risk of a 1,2 hydrate shift. Wow, it's only been a few days. You could do an oxymercuration, thank you, Justice, just a fraction too late. You could do an oxymercuration with mercury acetate, and you need some sodium borohydride to follow, and some water. What that does is it makes the Markovnikov product. So let's go ahead and make the guaranteed Markovnikov product. Oh, it's this enol. It's the same enol that we had before. And that will rearrange to give me the same ketone. Correct name for this ketone that we're building today is propanone, also known as acetone. Okay, that was one named reaction. What was the other named reaction? How about the reaction that generated the anti-Markovnikov addition of water across a double bond to make the anti-Markovnikov alcohol? What was that called? That was a hydroboration, thank you. If I do a hydroboration with B2H6 and peroxide and whatever else I need in there, I need a little bit of, I don't know, I need a little bit of acid. Then I purposefully made the wrong alcohol. What is the name of the product after this enol rearranges into its more stable form? What's that called? It's not propanone anymore. It's not an one. An one is a ketone because it has carbons on both sides. This is not an one, different family. It's no longer a ketone. This is now an aldehyde. And it is propanal. And to be able to change families from alkynes to aldehydes and from alkynes to ketones so easily is something that we're going to take advantage of. Yes, it didn't give me the diol, but having aldehydes is better than having diols. Learn as we go. Everything is interconnected. But aldehydes are a little bit reactive in their own right. And so they have a bit of more market value than alcohols or carboxylic acids. So this turns out to be a good thing. This unexpected rearrangement that we could have thought of as being a bad thing turns out to be okay. We're going to embrace it. Okay, well, I didn't see a lot of retention of material there. Perhaps that's a note to oneself. When is the next exam? Friday of next week, yeah. Do you think keto-enol tautomerism is going to be on it? Yeah. Yes, it is. Electrophilic additions is going to be a big electrophilic addition test. So we've got all the electrophilic additions to alkenes, the regular way, the Markovnikov description, the anti-Markovnikov description, and now doing it twice. Doing it twice to make the cis product, doing it twice to make the anti-product, doing it when it all goes completely wrong. It's going to go wrong in a way that we're happy about. All right, I'm going to show you a reaction now that we could have done for alkenes. And we can still go back and visit it for alkenes, but it's not as chemically interesting when we do it with alkenes as when we do it with alkynes. So I'll just do them all together. These reactions are hydrogenations. And a hydrogenation is exactly what it sounds like. You're going to add hydrogen. Let's start with an alkene. By showing a ring structure, and by having that ring structure have substituents on the alkene, I get to show you the mechanism of addition. Because we have two ways of doing the hydrogenation. The first is using a metal catalyst. We're actually going to take hydrogen gas and we're going to adsorb that hydrogen gas on a metal surface. So you've heard of this word before, absorb. But you may not have heard of this word before, adsorb. To absorb is like being a sponge, where you have some water spilled and the sponge absorbs the water into the interior of the material. Conversely, these walls have paint on them. The walls did not absorb the paint, because if they did, we'd need a lot more paint. They've adsorbed the paint. It only went on the surface. So absorb is when you take something into the interior. Adsorb is when it's only on the surface. So I'm going to take some nickel and I'm going to allow hydrogen molecules to stick to the surface. And crazily enough, they do. And when they stick to the surface, there is evidence that they actually split apart into hydrogen atoms. These are individual hydrogen atoms attached to a metal. That's going to make them be hydrides. Okay. Well, along comes an alkene, a double bond. And I think we can see what we're setting ourselves up for here. I'll do it to this one. Put that hydrogen, this hydrogen, both going to add to the same side. And so we end up having both of the hydrogens add to the same side of the double bond. The process is called syn. The product is called cis. So syn addition gives us the cis product. When you do this to something that's not fixed in a ring, it's going to be harder to see, because as soon as that double bond is a single bond, it's allowed to rotate. But it could have implications if one or both of those carbons is chirality center that you just made. And you could have real implications. Okay, we get syn addition across carbon-carbon double bond. Let's do that for an alkyne. I start with 2-butyne, and I use hydrogen adsorbed on nickel. Got a nice name. The great thing about chemistry is if you invent something, you get to name it after yourself. This guy Rainey invented this catalyst, so we call it Rainey nickel. It is going to make this alkene like that. To make the cis one, make the cis alkene. But that's going to react straight away with more Rainey nickel. And now all of our work is lost. So this we know it happens. We just can't get to it quick enough. We can't get that alkene out of solution quick enough to stop it reacting with another set of hydrogen. This is a metal catalyst, and it is very, very good at doing its job. So much so that the interesting part in the middle, we have to give up on. I'm not going to like that. I'm going to find a way to fix it. Okay. So this metal surface is what we would call a heterogeneous catalyst. It's a heterogeneous catalyst because our product might be in the liquid form, it might be in the gas form, but this is a solid. So we could consider a reaction that is liquids being stirred with some Rainey nickel at the bottom of the flask being moved around. Or if you're doing this as an industrial process, you might want to heat your reactant up until it's a gas, and then make a fine layer of the Rainey nickel solid catalyst, and then just blow the gas through it. Marcella, it means we know it exists. We might even see it for a fraction of a second. But the alkene, what we've done is we've put the alkyne in the presence of a metal catalyst. That metal is still in the flask. So after I've made this, it continues to react until it's not done, and until it doesn't want to react anymore. And at this point where it's saturated, it's done. So I go from unsaturated, still unsaturated, to saturated, at which point the reaction is over. This part in the middle, I can't get that out, which is what I have to invent next. Because this is intrinsically more interesting than that. Got geometric isomer. Telling me I can make something and it be the pure geometric isomer? Yeah. And then you lose it. I'm going to have to stop this reaction. I have to stop this reaction partway through. And the heterogeneous catalysts that we use are a little bit too good. Nickel So nickel's a metal, and you get it, you buy a piece of metal, and then you grind it down to powder. And then you just put it in the presence of hydrogen gas, and the hydrogen adsorbs to the surface. So now you have something that is really kind of dangerous, because hydrogen isn't flammable, explosive. And like a handful of this Raney nickel will hold enough hydrogen to blow the doors out of this room. Just break all the glass in this room. So it's a big thing. So once we've made the Raney nickel, we store it under oil so that nothing can get to it. Nickel is cheaper than the other metals that do this well. Nickel's not particularly cheap, but other metals that do this really well, platinum. Platinum does this really well. Platinum is expensive. So if your reaction required a gram of this, fortunately, you're going to be using milligrams of that. And then even better than platinum is this one. What anybody know what PD is? PD is palladium. And palladium is really, really good at holding on to hydrogen, but it's incredibly expensive. And so the small, like the speck of palladium that you would need for your reaction, it's ground up with graphite. So when you see the palladium being used, it's going to show you hydrogen absorbed onto palladium and then mixed up with a bunch of graphite. And these are, this one's good, that one's better, this one's the best. That's the cheapest. This is expensive. I don't remember ever using palladium and graphite, maybe once or twice. It's nickel before, because it's cheaper. It depends what your use is. What we really want is to be able to stop this reaction in the middle. There is another catalyst. And this catalyst contains a bunch of stuff. So much stuff that we don't need you to know what it is. Okay. It is some hydrogen adsorbed on platinum with some barium sulfate. Paint. This is paint. Okay. Barium sulfate is the white pigment that's in paint. And some quinoline. And all of this goes under the name Lindlar's catalyst. I don't need you to remember everything that's in Lindlar's catalyst. I do need you to remember what it does, how it's different. And if you just write Lindlar over the equation, that's good enough. Because Lindlar's catalyst does this. It takes the alkyne and it stops in the middle. This makes this catalyst quite useful. Okay, so now you can take alkynes and convert them into the geometrically pure thin addition product, which will be the cis isomer. This is the cis 2-butene. Is that the E or the Z? E or Z? Time to wait for the people at home. They got me answers before I could make a poll. Yes, that is the Z isomer. Okay, so when somebody comes along and says, I've solved your problem, I can give you the alkene in the middle. Now you can have all the cis 2-butene that you want. There is always somebody in the room that says, yeah, but I want the trans alkene. You cannot make the trans alkene with a heterogeneous catalyst. Heterogeneous catalysts are going to put both of the hydrogens on at the same time from the same surface to the same face or side of that pi bond. So what we need instead is a reaction that is not heterogeneous. We need something that is homogeneous. Something that is in solution with the pi bond instead of being something that the pi bond comes and rests on. What we do here Yes, it is, Justice, because of the platinum. It contains a platinum. So it's a metal. What we do here is we take some sodium metal and then we dissolve it in liquid ammonia. Now, ammonia is a gas at room temperature. In order to be in the liquid form, you have to make that pretty cold. You're going to be looking at -40 Celsius. I think the boiling point of ammonia might be 44. Let me just look that up. It's the boiling point. It's in Fahrenheit. 33. No, I don't believe that. I thought it was 44. Oh, 33. Okay. All right, so to get the ammonia to be that cold, you're going to need it to be a liquid. You're going to need it to be this cold, which means using liquid nitrogen to cool this thing down. Turns out ammonia is a really good solvent, but it's difficult to use because you have to use it cold. And one of the things that it does when it dissolves metals from group 1, you'll remember the group 1 metals have electrons around them. Then they have this one electron on its own It doesn't really want to be there. Because if you can get rid of that electron, you can be a closed shell. So sodium gives its electron away, and we make ionic materials with it. When you dissolve sodium in liquid ammonia, the electrons get solvated too. So I have free floating electrons in solution. You know what color electrons are? They ain't yellow. They're not red. They're not pink. Electrons are blue. At least they are in solution. In solution, electrons are blue. And this goes blue because it has solvated electrons in it. And it adds anti. The process of adding is called anti. The product is trans. With Lindlar, the process is syn. And the product is cis. So now we need two words, one for the product and its geometry, and one for the process in which it is made. Okay, I'm not going to start a new topic. There are two things that could possibly follow what's on the board right now. I'm not going to start them. We're basically out of time anyway. See you on Friday. I owe you some lab material, but I don't think I owe you anything from lecture. Tuesday people came in and did thin layer chromatography yesterday. I think Thursday's people, when they show up, are going to do a variation on that. So I have two different sets of answers, and we'll give that to you in order for you to problem solve. Okay. I'm waiting. You don't have to wait. Yes. Marcel, the process in a heterogeneous hydrogenation is always syn. That is, here's a double bond, here's a flat surface with the hydrogens on it. They're both going to add to the same side. Does that mean I always have a cis product? Well, no, not always, because if I gave you this, you can add hydrogens to here and here. There is no cis or trans for this because this only has hydrogens here. So to say that it's always cis is a little bit of a lie. The underlying reaction is always syn. The process of adding those hydrogens is always going to go to the same side of the double bond. And in the liquid ammonia and sodium, it's always going to go one in the top, one in the bottom. Okay? It's always going to be anti. Okay. All right, see you Friday.